Previously, we used integrals to find the volume of three-dimensional solids, which were formed by revolving two-dimensional areas around horizontal or vertical lines. Now let's shift our attention to looking at solids that are not from rotations. And the key for these solids is that the cross-sections are all the same shape. So now we will use integrals to find volumes of non-rotated shapes. And we will do so by taking an expression for the area of the cross-section of the shape. Take a look at example 6. This describes the Great Pyramid of Egypt. This is actually quite a fascinating topic, and you could spend a lot of time going down a YouTube rabbit hole learning about the Great Pyramid. But it was built over a 20-year time period, and we have the dimensions here. Its base is a square with a side length of 756 feet. And the height, when it was completed, was 481 feet. This is actually an incredible fact. It was the tallest man-made structure in the world for more than 3,800 years. That's incredible. What we're going to do with this problem is use cross-sections to find the volume of how much stone was used to build the Great Pyramid. So we want to start by drawing a picture. We have a square-based pyramid. Looks something like this. The dimensions of the base are 756 by 756, and the height vertically is 481. Now we're looking for parallel cross-sections that all have the same area. And there's actually a couple different ways we can do this, but I think the most intuitive way is to take cross-sections that are parallel to the base. Imagine just slicing horizontally here, taking horizontal cross-sections moving up the pyramid. So let's draw a representative slice in here. And once again, we're returning to this really key idea of integrals. Let's take a look back at that at the front of the handout. We're thinking of integrals as adding up slices of volume in this case. So if we can find an expression for the volume of a representative slice, then we can integrate to find the total volume. That's really going to be the key here, to think of slicing up the volume, finding the volume of a representative slice, and then adding up the volumes using an integral. So we will take cross-sections parallel to the ground. Here's a cross-section, just a representative slice. It's going to have some little bit of thickness, an infinitesimally thin slice, and let's just say that it's at some height h above the ground. So we have a distance h above the ground, and the thickness of this slice we will call dh. We're actually skipping over the Riemann sum here. We could be a little bit more rigorous, and we could call this first delta h. We could set up a sum and then take the limit to convert it to an integral, but we don't lose much if we just immediately jump to the infinitesimal dh. So if we can find the volume of this representative slice, then we can add up, we can integrate, starting from h equals 0 to h equals 481, and we will find the full volume of this pyramid. So now we focus on the volume of this slice. Well, this slice has some side lengths, and for now let's just call them s, because we don't really know what they are. And the slice is really a rectangular solid. It's a box, if you will, a very thin box. So the dimensions are s by h, by dh rather, and the volume of this box would be the product of the three dimensions. So the volume is s times s squared, times the height, dh. That's the volume of this slice. To get the total volume, I will integrate this expression, but I have a problem. I have two variables. I have s and I have h. So before we can actually integrate, we need to convert the s to be in terms of h. How do we do that? Well, we're going to do that using something called similar triangles. Imagine taking a cross section now vertically. Imagine slicing vertically into this pyramid. And if you do, you'll get a pyramid or a triangular cross section that looks something like this. The base here is 756. The height is still 481, the same height. And now we're looking at a slice occurring somewhere in the pyramid. The slice is at a height of h, and the width of the slice is S. Okay, let's talk real quick about the idea of similar triangles. If I have two triangles, I'll just draw a couple generic triangles over here. If I have one triangle with a height of capital H and a base of capital B, and then another triangle with a height of small h and a base of small b, as long as these are similar, in other words, they're the same shape, just different sizes. If they're similar, then the ratios of the corresponding sides must be equal. In other words, the ratios of the small sides, h over small b, that must equal the ratio from the big triangle, capital H over capital B. As long as we have the same triangle, just different sizes, ratios of corresponding sides must be equal. This is called similar triangles. So now take a look at our pyramid example. We have this triangle with the base of S, if we imagine this triangle here, and the height, well, from the ground to this slice, this was a height of H. So I want the height of this triangle overall, which would be 481 minus H. So in here, the height of this small triangle is 481 minus H. So I have a large triangle, this black one, with a base of 756, a height of 481. That is the same shape as this small red triangle with a base of S and a height of 481 minus H. So I can set up a ratio of corresponding sides. I'll start with the small triangle. S divided by 481 minus H, that's the ratio of these two sides. That's the same as the ratios of the sides for the big triangle. So S, that's the side length, that corresponds to 756. And then the height, 481. This relationship allows me to solve for S in terms of H. If I multiply both sides here by the denominator, 481 minus H, I have S equals 756 over 481 times 481 minus H. This is the value of S in terms of the height H. So I can use this expression for S, plug it in here to this expression for the volume of a slice, and then I will have a volume all in terms of H. So in terms of H, the volume of the slice would be 756 divided by 481 times 481 minus H. This is S, just written in terms of H. We want to square that, and we still have the dH. This is the key. This is the volume of the representative solid within this pyramid, the volume of the representative slice. So how do we find the total volume? Well, we integrate. The total volume is the integral. Think of the integral as adding up all of these representative volumes. The integral symbol adds all these up, so we integrate 756 divided by 481 times 481 minus H. All of this, once again, is squared in terms of H. And now what are the limits of integration? Well, we are integrating in terms of H. So we need to look at our picture and figure out how do we get all of the representative slices for the entire pyramid. H is the distance from the ground to the slice. So I need to start at H equals 0, at the first slice at ground level. So H equals 0 is the lower limit. And I need to keep adding slices until I get to the very top of the pyramid. Well, that height is the total height of 481. That is my upper limit of integration. So this integral is describing the volume of this great pyramid. Now, this isn't actually too bad to do by hand. We could square the 756 over 481, take that out front, and then we'd be squaring 481 minus H. We could expand that out. We're actually integrating a polynomial. So we could expand that out, find the antiderivative, but that's a lot of busy work, so let's just go ahead and plug this into Mathematica and see what we get. So if we type this into Mathematica, here's our integral, and if we select Enter, we get 9.16 times 10 to the 7th. This is the measurement of the volume of the Great Pyramid. Now, all of the units were in feet, so this volume measurement is cubic feet. This is 91 million cubic feet of stone. That's an incredible amount of material. So for the answer here, we would write approximately 91.6 million cubic feet. That's a lot of stone. Let's use this idea of cross-sectional areas to solve problem 7. Problem 7 is interesting because here we're going to find the area. We're not actually doing a volume problem, but the concepts we use to talk about area here will carry over for the next problem. So we want to use cross-sections to find the area of a circle with radius r. What on earth do we mean by this? Well, let's give it a try. Let's see if we can figure this out. First, I'll draw a circle. The radius of this circle is capital R. Now, I want to divide this circle into cross-sections that are parallel in some sense. And this is going to seem a bit strange, but what I'm going to do is to take circular cross-sections. I'm going to imagine taking a circular cross-section within the circle of some little bit of thickness. And let's say that this is at a distance of small r from the center. And this thickness of this little slice of the circle we'll call dr. So dr is the thickness of this. Okay, we're just taking this band. We're not taking anything inside. We're just taking this band of the circle. It's a thin slice of the circle. It's hollow, and we want to figure out what is the area of this thin band. If we can figure out an expression for the area of this band, then we can figure out the area of the entire circle. So we want the area of one of these circular slices. Well, I'm going to imagine taking this slice, removing it from the circle, looking at it a bit closer, and I'm going to imagine just cutting it like this and then flattening it out. I get a roughly rectangular shape. And what is the distance here? Well, that's the distance all the way around this circular slice. So that distance would be the circumference of this circular slice. And the circumference is 2 times pi times the radius. So the circumference here is equal to this length. This would be 2 times pi times the radius. And what is the height? It's the thickness of this slice, dr. So the area of this slice, well, if I remove it from the circle, flatten it out, then I really get this rectangle. And it has dimensions of 2 pi r by dr. So the area of this slice is 2 pi r times dr. That's the area of one of these slices. Now, how do we get the total area? We integrate. Once I have a representative slice, I integrate, I add up all these values to get the total area. So I integrate 2 pi r dr. And what are the limits of integration? Well, I need to get all of these circular bands throughout the entire circle. So I need to start at a radius of 0. Notice that I'm integrating with respect to r, this variable radius. So that must start at 0 to get the very center of the circle. And then I need to add up area concentrically until I get to the exterior, which would be the full radius, capital R. All right, can we solve this integral? Well, sure we can. 2 pi is just a constant, so we can take that out front. So we have 2 pi times the integral from 0 to capital R of r dr. Antiderivative of small r is r squared over 2 times 2 pi. Integrating from 0 to capital R. First plug in capital R, we have 2 pi capital R squared divided by 2 minus 0 squared divided by 2, which is just 0. Notice that the 2's cancel, and we are left with pi r squared, which is exactly the area of a circle with radius capital R. I think this is a really neat example of using an integral to solve a geometry problem. We just proved that the area of a circle is pi r squared, and the only thing we needed to prove it was the formula for the circumference. Let's take a look at this in Desmos to see if we can visualize better what's going on here. So here we have our circle of radius r, and we're imagining taking concentric bands, something like this. So we're taking the area of all these red slices and adding up all the areas of these red slices, starting at a radius of 0, going all the way to the exterior of the shape, adding the areas of all those red slices. The limits of integration are from 0 to capital R, And all those slices added together give us the full area of the circle. Let's work through example 8. We are going to find the radius of a sphere with a general radius r using two different methods. The first method will be the volume of rotation that we discussed earlier, and the second method will be a rather interesting use of cross sections to find the volume. So we'll find the volume in two different ways, and I think the interesting element of this problem is that we can get to the answer with two very interesting methods. Okay, so first, let's think of doing a volume of rotation. So we'll start by sketching the two-dimensional area. The function that we're working with is y equals the square root of capital R squared minus x squared. If you graph that for different values of r, we will have a half circle in the upper half plane. So it looks something like this. This distance is r, so is this distance here. And if we imagine rotating this graph around the x-axis, we can imagine getting a sphere with a radius of capital R. Well, how do we find the volume? In this case, there's no inner hole, so we have just a solid region that's being rotated around, and the radius of this region, in terms of x, is just the y value of the function. So this expression here is our radius function. So the volume is the integral of the radius function squared dx. We'll put an a and a b, and this is all multiplied by pi. So in this case, we have pi times the integral, and the limits now are from negative r to positive r. In order to get all of the area here rotated around the axis, we need the limits to be from positive to negative r. So we integrate from negative r to positive r. Square root r squared minus x squared, and we're squaring that. Well, this is convenient. We square the square root, and those go away. So let's go ahead and solve this integral the rest of the way. We have pi times the integral from negative r to positive r, capital R squared minus x squared dx. All right, capital R squared is a constant, and we have minus x squared. So taking antiderivatives, we will have pi times capital R squared x minus x cubed divided by 3, integrating from negative r to positive r. So we have a bit of algebra to deal with here. We're first going to input the positive r, and then input the negative r, subtract the two, and let's see what we get. Replacing x with positive r, we have positive r cubed minus r cubed divided by 3, minus, in parentheses, r squared times negative r, so negative r cubed, and then replace this x cubed with negative r. That'd be negative r cubed, but we're subtracting, so we get a plus r cubed divided by 3. All right, for the next step, we have pi. We have an r cubed minus minus r cubed, so plus r cubed. So let's turn that into a 2r cubed. And then minus r cubed over 3, minus r cubed over 3. That's a negative 2r cubed over 3. So minus 2r cubed divided by 3. And let's get common denominators here. I can write 2 as 6 divided by 3. So if I have 6 over 3 minus 2 over 3, that will be a 4 over 3 r cubed. So the final answer here is 4/3 pi r cubed. And hopefully you recognize this as the volume formula for a sphere with a radius capital R. We can arrive at this geometric formula just by using an integral and taking the appropriate function for a circle, rotate it around an axis, and here we have the volume for the sphere. I think this is pretty great. We can find a geometric formula using the power of calculus. Just because it's really cool to view these in 3 dimensions, let's go ahead and look at a 3-dimensional visualization of this. So here we have the graph of the square root of capital R squared minus x squared. And now if we imagine spinning this graph around the x-axis, we get this beautiful sphere. So using the power of solids of rotation with calculus, we can find the exact volume of a sphere. Now let's find the volume of a sphere using a different approach. We'll get the exact same formula, but we'll have a different integral to set it up, and we'll have a completely different way of thinking about the problem. Let's find the volume by taking spherical shell cross sections. What on earth does this mean? Let's try to draw this out. So first of all, let's just think of drawing a sphere. Here's a sphere. Not a very great drawing, but there's a sphere. It has some radius capital R. And I want to imagine taking spherical shell cross sections. So I think the best way to visualize this is really to think about an onion. If you think about an onion, it has these concentric spherical shells. And we're going to take one particular shell. So here's one shell that's inside this sphere. And we're not thinking of this as a solid sphere. We're not thinking of a volume here inside, but rather we're thinking of the volume of the shell. So this is going to have some little bit of thickness, just like an onion ring might, or maybe if you can think of a tennis ball, that might help as well. But we're going to find the volume of this spherical shell. It's hollow inside, so we're just really finding the volume of the material that's consisting of the outside. So really, if you think of a tennis ball here, we're finding the volume of the felt-covered rubber. We're not finding the volume of the interior hollow section. That's what the spherical cross-section means here. So let's imagine taking a spherical cross-section that's a distance, let's say r from the center. So we have a radius r. And if we can find a volume expression for this spherical cross-section, then we can integrate to find the total volume. So we want to know what is the volume of a slice. And the slice here is this spherical cross-section thing. Now, just to make sure that we're able to visualize this well enough, let's take a look at a three-dimensional plot. So here we have our overall sphere. This has a radius of capital R, and we want to imagine taking smaller spheres, spherical cross-sections inside. So here's a small one, and then we want to imagine growing these cross-sections, getting concentrically larger. We'll find the volume of all of these hollow shells, and then if we can add up all of the volumes of those shells, that will find the entire volume of the solid sphere. So think of taking an onion, and if we could unwrap it and take out all of the spherical concentric shells, add up the volumes of all the shells, that would give us the volume of the entire onion. That's the approach that we're taking here. It sounds strange to slice this sphere up spherically with these spherical cross sections, but this strategy will totally work to find the volume. So now we want an expression for the volume of this slice. How do we find this? Well, this is going to be the surface area of this spherical slice times its thickness. So we're going to take the surface area in here of this spherical slice and then find the thickness. The thickness is some little change in the radius. The thickness here we can call dr. That's how thick this slice is. So the volume we can find by taking the surface area times the thickness, dr. Surface area of a sphere is 4 pi r squared. So this expression gives us the volume of one of these spherical shells. How do we find the total volume? We integrate. To find the total volume, we add up or we integrate all of these representative volumes, 4 pi r squared dr. What are the limits of integration? Well, we need to start at the center of the sphere, so we start with a r value of 0, and we need to grow these cross sections until we get to the full size of the overall sphere. So we go from 0 to capital R. Can we integrate here? Yes, we can. 4 pi is a constant. We're really focusing on r as the variable here. So our antiderivative is 4 pi r cubed divided by 3, integrating from 0 to capital R. Notice how we get a different integral than the last one. Now we plug in capital R, 4 pi capital R cubed divided by 3, plug in 0, but that's just 4 pi times 0 divided by 3. So our final answer, once again, is the volume of a sphere, 4/3 pi r cubed. I think this is fascinating. We can obtain this geometric formula using two different approaches. We get two totally different integrals. I think this integral is actually easier than the last one we did, but both of them work. We can get to the volume of a sphere either way using calculus.